In this lesson, we shall focus on mathematics, MATH141 Calculus UKZN module. We shall be looking at a wide range of the tutorial questions, but also their applications, techniques of integration, and a lot more. Right, we actually take a look at the questions, some of which we went through. For example, we went through this particular question and we solved it together. So we are moving forward to the kinds of questions that need to be done right now. Okay. We solved these particular questions to A, B, and C. We solved to D. Yeah, we also did this one to E as well. Right, we also did 2F. We went to try 3A. We did 3A. Okay, we did question 3A, and this became the solution to the problem here. We continue. We did the question 4A of the arc length of the curve y equals the ln of x. Right, now we need to start on the partial fractions. Let us do some questions on the partial fractions. And then we shall mix with the other topics also so that we have a sense of what is happening everywhere. Right, looking at the partial fractions, we have, for instance, 6a, the integral of 2x squared, 7x plus 3 divided by x plus 1 cubed. And then now, to deal with this, first and foremost, we look at the degrees. Right, if you look at the top is quadratic and the bottom is cubic, meaning that this fraction here is a proper fraction because the denominator is bigger. It's of greater degree 3, and this one is of degree 2. Right, and if you look at this, then we can be in a position to write these as follows. So we actually clearly see that we have 2x squared with 7x plus 3 divided by x plus 1 cubed. And then now we need to actually look at the denominator and reason very, very carefully in terms of how the denominator needs to be written out. But just that we look at the denominator basically, but the denominator is cubic. Right, if the denominator is cubic, we need to actually therefore be conscious of the fact that we need to first write a divided by x plus 1. Right, so we write these in the increasing powers of the denominator. Right, and in increasing powers of the denominator, we're able to make a couple of observations. Right, so we shall have the following in just a split second. Okay, now we need to write this in the increasing powers, but this is something I want to bring to to the surface here, and we shall discuss the actual technique that must be used here. Right, in as far as what we call the partial fractions are concerned. Right, and so if you have the 2x squared, okay, there's a little trick that we need to use here so that we're able to get the correct result. Right, there's a little trick we need to use here so that we're able to get the correct result. So if you have the 2x squared together with the 7x plus 3, right, so what then we need to have becomes exactly the following, yeah? A over that, b over x plus 1 squared, c over x plus 1 cubed, like this. Okay. And now, at this point, we multiply through by the denominator. Right, and if you multiply it through by the denominator, we're able to get exactly the following. So we take the 2x squared plus 7x plus 3. You divide by x plus 1 cubed. You cube it, which is a over x plus 1. B over x plus 1 squared. You multiply by the cube. C over x plus 1, you cube it. Which is 2x squared plus 7x plus 3. Which is a, then we have x plus 1. Squared plus b, then we have x plus 1. Okay, because the x plus 1 cancels a single factor of x plus 1, giving us a square. And then you have c, like that. Okay, so we have seen here the x cubed cancels the x cubed. We multiply by the LCD, lowest common denominator. Right, and if you multiply by the lowest common denominator, that is what we're able to achieve. So x plus 1 cancels now, giving us 2 there. The 2 cancels out, giving us a 1. The 3 cancels out, giving us power 0, or just a constant. In which case, therefore, we're able to make the observation that we have 2x squared plus 7x plus 3 equals that. We have 2x squared plus 7x plus 3. Continue. Right, so we have 2x squared plus 7x plus 3, which equals a, which is exactly x plus 1 squared. B, x plus 1 plus c. 2x squared together with 7x plus 3. X squared plus 2x plus 1. X plus 1 plus c. Plus 3. Ax squared is there. Then you have the a 2x and the b, which means that we shall have exactly 2a plus b, which are linear terms. 2a and b, then there's common factor x. Then there is an a, b, and c. Right. So a is 2. 2a plus b. Yeah, 2a plus b. A plus b plus c. Okay. Now, if this is the case, a is 2, then we have 2a plus b equals 7, which means b equals 3. Right. So that in the end, then a is 2. B is 3. Okay. So now c becomes -2. Right. So by comparing the coefficients, we have a equals 2, we have b equals 3, and c equals -2. Which therefore means that whenever we have the 2x squared plus 7x plus 3, you divide it by the perfect cube of x plus 1. You said it is a over x plus 1, b over the square, the cube. Okay. What is a? It is 2 over x plus 1. B out of 3. Now the b is 3, x plus 1. And then and 2 over. Okay, this one is squared and this one is cubed. But this middle term is squared. So then the integral x plus 1 cubed. The integral of the following. 2 divided by x plus 1. So integrate this first one. Also integrate the 3 over x plus 1 squared dx. 2 over x plus 1 cubed dx. To the ln of x plus 1, integrate the middle one. Okay, the integral of this one, you're going to do it like, because the derivative of the x plus 1 within the brackets, it's a 1. So you use the same rule as when you're integrating u to the minus 2 du. And now this one becomes 1 over minus 2 plus 1 u to the minus 2 plus 1 plus c. And therefore, this is minus 1 to the minus 1 plus c. And it is minus 1 over u plus c. Right, so if you come to this one, it's the same thing. The derivative of the u plus of the x plus 1 is 1, meaning that since the derivative of what is within the parentheses, the variable expression has derivative 1, and therefore you shall have that the integral of this is going to be minus 2, but there's minus 1/2 x plus 1 okay, so in the end, then what is the integral here? Therefore, we conclude that the integral of 2x squared 7x plus 3 over x plus 1, you cube it, to the ln of x plus 1, 3 over x plus 1. And then this one here is plus 2 over 2 is 1, which is 1 over x plus 1 squared, plus c. Yeah, take a look at that one. Take a look at exactly that one there. Okay, take a look at exactly that one there. Any question? I believe that is very clear. We move on to the next question. Okay, yeah, we said we're going to pick. Let us do something else now. Shall do that. Let's check. Okay, that's fine. Okay. D, right? Okay. Let's see. Okay, I'll depend on you. If we need to do B, I'll depend on you. If we need to do B, C, D, okay. Okay, because I need to stick to your comments and make sure I understand you. Okay, so not D, but F. We think you need to do F, okay? I'll assume that. Right, we can do F. Good, now F is a bit different. We shall even get to F. Using the method of partial fractions. Right, and then using geometric substitution and the method of partial fractions. Let's do 7. Let me see. Okay, we shall go back to some of these things. We have 2 the square root of e plus 1 x over x squared minus 1. X minus 1, x plus 1. B over x plus 1. Now you multiply everything. So if you multiply everything, x plus 1b, you have x minus 1. Right, and then this becomes exactly x. A plus b, x, because you have ax and bx, a minus b. A plus b is 1. A minus b is 0. So that a is b. So a is 1/2 and b is a, and it is 1/2. So that when we need to integrate this one, we'd have the integral of this. And then the a is 1/2. The b is 1/2. Right, so if you check, we start from the margin, the integral of this. Yes, please.
Yes, I got lost in the part where it says A plus B is equal to 1 and so on. So yeah, I got lost on this point.
Okay, that's fine, because we comparing the coefficients. So now, obviously, if you look at the ax and the bx, so we're able to get ax and bx giving us a plus bx, but the coefficient of x here on the left is 1. So that a plus b is equal to the coefficient of x by comparing coefficients. So a plus b is 1, the coefficient of x. And also a minus b is the constant term. And there's no constant term, so the a minus b is 0. So that now we have a equals b. So that a equals b equals 1/2. So that now 2a equals 1, and then a equals 1/2. Then if 2a here, because we know that a minus b equals 0, a minus b equals 0 because there's no constant term here. So a minus b equals 0, which means a equals b. If you put a equals b, so wherever there is a, we put b here. Wherever there is b, we put a, so that a plus a is 2a, and then a is 1/2. But a equals b, so a equals b equals what? Because a is 1/2, therefore a equals b is equal to 1/2. Okay, we come to this, the integral of this. we have the ln of this. Okay. So you have e that. So that you have 2 the integral so okay, dx, and then we have 1/2 plus 1/2 the ln of this, and then it is 2 to the square root of e plus 1. And at this point, we plug in everything. We plug in the square root of e plus 1 so that it is exactly 1/2 the ln of the square root of e plus 1 in the place of the x, then subtract a 1. And then you have this one. So right, okay, yeah, let's go back. So you have this one, okay. So we have this. But now looking at this, you're able to see that it is exactly this. So what it suggests is the following. Okay, look in the answer. I mean, it's the same answer that you can simplify. But because looking at the answer, you can just make it very similar. You can pull out the 1/2, then you have the ln. Now there is x minus 1 and there's an x plus 1. So okay. You have the ln. So when you have the ln, let us write at the bottom. Okay. So you have this. Okay. And therefore, this one here is exactly 1/2 the ln of the square root of e plus 1 minus 1. 2 squared is a 4, minus 1 is 3, ln 3. Okay, let's take a look at this one. Right, taking a look at this one. This is the minus half ln 3, it's there. So we have used the method of partial fractions. Right. So if you've used the method of partial fractions, that is what we are able to achieve here. So we have used method B, and there's a clear observation that this one is actually going to be exactly 1/2. So, but obviously you can look at whether that is the case. Check if that is the case. Check if that is the case. Right, so okay. Right. It will be very interesting to see that this here becomes exactly a 1. Becomes exactly a 1. Okay, we're gonna check that, but let's use a suitable substitution in 7. Yeah, because the answer is this one is 1/2. It may just arise that way. We'll check that. But if you have 2 to the square root of e plus 1, then you have x squared minus 1 dx. Let u be x squared minus 1. Du it's 2x dx. Right, so with ux, so we have e plus 1. So that in the end, okay, first you have x and the u. Okay, let's check the x and the u. I want to effectively then say you're going to have here the x and the u. Let's check x and then u. X itself, 2 and then the square root. Okay, u is that, and if you put the u, the x here, it's going to be 2 squared minus 1 because x squared minus 1, which is a 3. We put this one here, and therefore it's going to be, if you square the square root, it's going to become exactly e plus 1 subtract, and then it becomes an e. Right, so that this integral here is going to actually, instead of running from 2 to that, it's going to run from 3 to e. U dx. Which is the u divided by 2x. Which is du divided by 2x. Which is 1/2 the integral from 3 to e. out of 2 from 3 to a. And then you put, okay, yeah, the integral of the 1 over u is the length. So this one is going to be exactly, is the 1/2 there, but it's going to be 1 over u. Du, which is 1/2 the length of the modulus of 3 to a. 1/2 the length minus the length of 3. Okay, yeah. Because the u is 3, substitute the 3 there. The length of that is 1 minus length 3. Okay. Okay, this is what you have. So you have exactly this. And this answer is 1/2 minus 1/2 length 3. So that is the answer we're getting. That is exactly the answer we're able to achieve. Okay, it's a 1/2 minus 1/2 length 3, and it's very interesting to see that. Okay, yeah, take a look here. I think we made a square there. From the x squared minus 1, we needed a square there in that. In which case, I was wondering why it looked different. So you then have the ln. If you square the square root, it goes away. Two squared minus 1 is a 3. And then it's a. Okay, so 1/2 minus 1/2 ln 3. So the 1/2 minus 1/2 ln 3 is therefore the correct answer. So even if we use the partial fractions, we get that because we started here. Right, the x of x squared. So yeah, the a part. So in other words, you started with b because b said by method of partial fractions. And we then said, obviously, a plus b is a 1 because we're comparing the coefficient. The coefficient of x is 1 there. And we're able to get that a is half, b is that. Okay, so we get 1/2 minus 1/2 ln 3. And then if you have this one here, 1/2 minus 1/2 ln 3. So we continue to do this one. Okay, we shall go back to the partial fractions, please. But I want us to look at the improper integrals. Now, if you look at this improper integral, I know you might have been doing them. So from e to infinity, the limit is b. So we have e with that ln x. dx. Ah, so in the end, you let u.
Sorry.
Yes, please.
Yes, may you please explain like what's the concept of improper integrals? What's the concept based on the improper
Okay.
integrals?
The improper integrals. The improper integrals, we always convert them to the limit. Always. We convert them to the limit. And now we try to avoid a situation where there is a limit of integration that is infinity or minus infinity. We're able to see that at the top that there's a limit of integration that is infinity. So we're going to change it. We're going to make it b. We make it a variable, but often b. And then now we then take the limit as b approaches infinity so that we still have the same situation because b can be replaced by infinity, but we replace the limit of integration by b to make the integration possible. Right. Okay, we're going to see exactly that. So we always replace the one limit of integration by b. The upper limit normally by b, but you can also replace the lower limit by b as well. So here we can integrate, we're going to replace with b, but it's going to be minus b to b. Let u. So we have this one, 1 over x dx. So what is dx? Dx is x du. Yeah. Okay, so we have the limit right now 0 to b. Yeah, but now you just need to do the integration first because this kind of a problem requires us to integrate this. So the best is to avoid problems. Let us do the integral first and not take into account the limits of integration. So we're going to look at 1 over ln x and then the 3. But now, so that we have u, then dx is what? X du. Just left the limits of integration out. X cancels. We have the ln of that plus c. So that the u is the ln of x. Oops, there's a cube there. Yeah. Oh, you wanted to see you're seeing the cube here. Right. Okay. Okay, well done. So there's a cube there. And because it's a cube, what is the integral of this? Then the integral of this becomes 1 minus 1/2. And then you can write 1 over u squared. Yeah. like this, plus c. Because it's minus 1/2 and then u to the minus 2. In other words, we're saying the integral of u to the minus 3 du u to the minus 3 plus 1. Minus 2 plus c. Okay. The u. And the ln of x cubed plus c. Okay, we're getting this answer, and obviously you can already check it out in the charts to see if it's exactly the same answer that we have, or it's actually different. So we continue. We continue. Right, so take a look at that and check in the chart. But also you see these problems. Okay, remember this is still just the integral, but we need to still substitute the limits of integration. Right. Okay. Also, you need to check if this is correct. One over the ln of x, like that. So d dx. Right, and then you'd have the ln. So find the derivative of this, which is actually exactly 1. Which is actually then you subtract a 1, you get a minus 3. Okay, I'm just checking the answer by differentiation to see if it gives us back that, because I don't want to continue with an answer that has been obtained by mistake. So that's what we get, and then the derivative of the ln is 1 over x. Right? So we continue. Right. So we continue. So that now you integrate. You write the integral from e to infinity. This one, 1 over x, the ln of x cubed And then now, we have this one here. Dx. The limit as b approaches infinity. Right. Okay, this integral the integral is minus 1/2 the ln of x squared. So this integral is minus 1/2 then 1 over the ln, right? 1 over the ln of x squared, but you can put the square in the denominator like we did. Like that. So that 1 over the ln of x squared. And then obviously we integrate from e to b. B approaches infinity. You have the ln of b squared minus 1 over the ln of e. And then you have this. Okay, as b approaches infinity, okay, there's a square here. There's a square there, and then there's a square there. B approaches infinity, so this one is going to be what? B approaches infinity, this one is going to be 0. Yeah? When b approaches infinity, this one is going to be 1 over infinity becoming 0. But this one here is going to be exactly a 1 in the denominator, giving us a minus 1. So we have exactly that. We have exactly that. We have exactly that. Next, let's do B. It's easy. Can just do it fast. B can be done really fast. So obviously you have the tart, and then we can be able to check the tart there and see what we're getting with the tart. Right. So if you look at the integral, x squared plus 4 dx, till we have the limit b approaches infinity. Okay. So, okay, yeah. Take a look at these and then reason. But the number 4 is the one to sort of watch out. But the number 4 can be as 2 squared. So you can write the number 4 as 2 squared. And then use the fact that the integral 1 over x squared plus 1 dx. This integral is arctan of x plus c. Okay, so take a look at that one. So that you have x squared plus 1 so we have the limit of the following. So now, because you look at the fact that the 4 is 2 squared, and the integral of x squared plus 1 of 1 over x squared plus 1 is arctan x. So this one, the 2, what we do with the 2 becomes the following. Arctan of x over 2. Okay, but obviously we have the limits. Write it out. Be that. So this is 1/2. And then you have minus b to 2. And then this is the limit right, which is arctan. The x is 2 out of 2. Minus b over 2. So with the limit, b approaches infinity. Okay, this is step 5, just discussing improper integrals. These are called improper integrals of the first kind, where we just replace the limit of integration by b, but obviously here there's going to be a minus b. And with this, and then 1/2 and then arctan 1. Okay, the negative can go through the tangent. The tangent is an odd function. Even the arctangent is an odd function. Here's the limit. 1/2, which is pi over 4 plus arctan. One half the plus arctan that. So now you have to look at the fact that arctan of infinity, right, need to look at the fact that arctan of infinity is actually the pi out of 2. It's actually the pi out of 2. Okay, we'll check this one. So we have here minus infinity, and then it is minus infinity to 2. So this one is 1/2, and then this one is exactly pi out of 2. Because the tangent is undefined at 90 degrees from school. So if you put the infinity here, it's going to be arctan infinity, which is pi over 2. You multiply by 2, multiply by 2, it becomes pi over 4, 2 pi over 4, which is 3 pi over 4. It's 3 pi over 8. Um, okay, so okay. Okay, so this is the answer. So think about it then, but that is the answer. But yeah, this is quite short. The answer has been done just on the same board. C can be done in a similar manner. Also, C is very easy and short. We look at C now. Now to do C, we would take the integral from minus infinity to infinity of x divided by x squared plus 5 squared dx. And then you have the following. Like that. Okay, continue. Okay. Now at this point, you do the same. The integral of this one, when b approaches infinity, then you have this. So you to do the integral, or just do the integral quickly. It's very easy. Just leave out the limit of integration for now. You let u be x squared plus 5. And this means the u is 2x dx. X over u squared. Dx is du divided by 2x. The integral of the x cancels here, giving us 1/2. du. So 1/2 u to the minus that. So if you have the integral of minus 1/2 the u x squared plus 5 plus c. Okay. Okay, here the integral of this. And so you have this, and then so the integral of this x of x squared plus 5, wherever there is x squared plus 5, you put a u, whose derivative is 2x dx. And then dx from this becomes du over 2x. du over 2x. X cancels, giving us 1/2 that. So obviously, what we're saying here, we have the 1/2 and then the integral of the u. The u to the minus 2 is u to the minus 1, and that. Which is minus 1/2 and then 1 over that. So in the end, then the integral of this x over x squared plus 5 whole squared is the same as this. And then you have this, which is minus 1/2 which is 1 over b squared plus 5. And then you put the minus b, you square the minus b, is going to be just, okay, you can put the minus, but it's going to just be b squared plus 5. B squared plus 5. Like that. So that now you have the limit of this as b approaches infinity. Right, so this one appears to be such that it's going to converge to 0. Yeah? Okay, so continue. We continue. So, okay, I'm trying to check the chart also. So that as B approaches infinity, it's going to be infinity. 1 over infinity is 0. 1 over infinity is 0. Yeah. Okay. Then that is what we get. So this limit of this one is going to be exactly 0. Check that. The C part, yes, it is 0. Now there's sort of divergent limits. Okay, I'm going to look at the rest of those. And like the integral of the 1 over the cosh, we shall take care of that one. Okay. Now, the kinds of integrals we talked about now, with these 3 integrals here, are actually called. These are called because this answer, this one is 1/2. You saw that. Also in the chart. This one is 3 pi of 8. You saw in the chart. So it's fine. In the chart tutorial. And then also this one is 0. And you saw it in the chart. So in the end, we have the following. All right. You have the integral or the next one. We have done the C. Okay, these are called improper integrals of the first kind. Of the first kind, because they are. How do you see improper integrals of the first kind? We see the limit of integration that is infinity. Okay, I'm gonna do this ones also. Like this one. Doesn't matter. Can do any of these. But maybe before I do this, because I've already sort of elaborated on these improper integrals, I want us to look at improper integrals of the second kind. Improper integrals of the second kind. So all these behave in the same way. Like this integral of 1 over the cosh. Can just do that one, is very nice and short. Right. Very nice and short. Okay, yeah, we're gonna do that one in a split second, but now take a look at that and think carefully and see how best this can be done. Right. So we continue. Right, so right, this is what we are able to get at this point. So if you have this particular integral here, okay, it can be done in several ways. So you can use, you can consider the integral of, for instance, the such. So this is the limit. Yeah, okay. I'm just matter which one we do. You can do h, and then we shall go back to the others, please. It doesn't mean that we're just leaving them. But so okay, so in the end, then you have dx divided by that. Okay. So this is the limit. Okay, then we have minus b to b. Which is the sec of x dx. So now, what is the integral of the sec? The integral of the sec is the arctan. Now, this one you can see one way of writing that is the arctan of the hyperbolic sine of x. The integral of the sec of x. Right, the integral of the sec of x. Right, so the integral of the sec of x is exactly that one there. It is exactly that. Right, so we continue just now, but now take a look at that. So in the end, then we have the following. We have exactly that there. We have precisely that. Okay, we're going on. Please, we're still here. We're still there. So the integral of this is actually exactly that. But now, you see, I'm pausing because there are too many presentations of this integral here. So it's not just one type. But I'm also pausing because you might have done these differently, and there are like too many results of this particular integral here, and you might have done it using another method. So yeah, but this is, I think, the best, the most popular. Okay. So yeah, the integral. So in other words, if you have the 1 over cosh is the sec of x hyperbolic secant, whose integral is this? So in the end, minus arctan of this one. Okay, so as b approaches infinity, you'd have, okay, now you have the hyperbolic sign. Okay, so this one is octane. The hyperbolic sign is what? What is the hyperbolic sign of this? Right, so the hyperbolic sign of this, you remember that the hyperbolic sign of b is e to the b minus e to the minus b out of 2. So that you have exactly that. So that in the end, then if you take this at infinity, it's going to become what? It's going to be e to infinity minus e to minus infinity out of 2. Okay, let's continue and check this out. Octane. Okay, now the hyperbolic sign okay, here is e to minus infinity minus e to infinity divided by 2. Octane. Okay, now this e to minus infinity is going to be 0, but e to infinity is going to be infinity out of 2, giving us infinity minus octane. E to the minus infinity is 0, and this is minus infinity. All right, so yeah, we're in business now. What is octane infinity? It's 90 degrees, and this negative goes through here, giving us exactly another 90. But pi over 2 plus pi over 2 is pi radians. So yeah, that one is going to be exactly pi radians. Checking the chart also. It's going to be exactly pi radians. It's going to be precisely pi radians. Yeah, check it out. It's going to pay. Okay, you see, we're going to go through the other questions, but I'm just highlighting the different ways of like doing the different questions that look very different. Right, so yeah, in the chart, you can see that problem H has the answer pi. Now, I want to do more problems that look very different, but I want us to do two right now. I want us to do two right now. Okay, I want us to do two right now. Okay, let's look at this number two. Number two is also an improper integral, but now I want to do also these problems which are look very different. But how to do this one? Okay, we have to spend time on the other questions, but sometimes I'm just like picking randomly. Um, okay. Okay. Right. So what then do we do here? Okay, now you're dealing with the improper integral of the second kind. These are called improper. All right, these are called improper integrals of the second kind. Okay, now let's take a look at the improper integrals of the second kind. So at this point, we pause to reason together. So we have the following. Okay, so this kind of integrals now, they aren't defined at the limit of integration, maybe like at pi over 3 radians, pi over 2, but this one, for example, at pi over 3, you're going to have that cosine pi over 3. If you substitute pi over 3, cosine 60 degrees. Okay, let's write it like that, cosine pi over 3. Okay, and so we continue. So now we look at this integral here and we reason together. We reason. This one is undefined at pi over 3. So in other words, if you have the integral of from pi over 3 to pi over 2 of the sine of x over this. Cosine x dx. Think with me. Okay. Now, to reason this out, so we need to draw a lumber line like this. So that in the end, then you have pi over 3, pi over 2. Okay, so if this is pi over 3, then this particular integral, where is it undefined? It's undefined here. All right, it is undefined there. It is undefined at pi over 3, because that is when this one is cosine of pi over 3, it's actually 1/2 in the square root. We put 1/2 here, and it is 1 minus 1, and then 0. Okay. So the denominator becomes 0 at pi over 3. But you see at pi over 2, then cosine 90 degrees, cosine pi over 2 is a 0, so that it's 1 under the square root. So that then what we're able to achieve here becomes the following. So what we have becomes exactly what? Okay, you need to reason that it is undefined here, and the only way for us to integrate this successfully, we need to consider this lower limit of integration. And we consider this lower limit of integration, we must sort of bring an adjustment to a position that is within this interval. That is within this interval. If we're here also, if it's undefined here, we're going to bring it here. So to bring it there, we need to add an epsilon, pi over 3 plus epsilon. Yeah? So that in the end, we have pi over 3. So we have this. Okay, we have exactly this. We have pi over 3 plus e, pi over 2. 2 cosine x dx. Okay. This is what we do. So we add to the bottom limit of integration, we add an epsilon. Because we can explain here, since f, there's a function f, which is this one, the integrand. So if this function being the integrand is undefined, since f is defined, right, so f itself becomes defined on this. It's defined on, okay, yeah. It is defined on pi over 3 to pi over 2. Okay, so it's defined from pi over 3 to pi over 2. But now look at the bracket is round here, because this improper integral is actually not having a limit of integration that is infinity, but it is undefined at one of the limits of integration or within the interval of integration. Right. But yeah, it is undefined pi over 3, so we must remove pi over 3. So it's defined there. And let me push it up like this. I want to write a bit more. I want to write a paragraph here that explains our position, and then we shall move on. So this is edit like this. Since okay, maybe I can, yeah, that's fine. Since f is defined, it's defined on pi over 3 to pi over 2, round square. Is defined on that. And Riemann integrable on, right, so it becomes a Riemann integrable on pi over 3. If we want to include it, then pi over 3 plus epsilon. To B, this is true for 0 less than epsilon less than. Okay, so yeah, pi over 3 to 2, that's what I mean here. So pi over 2. And then pi over 2 minus A like that. Okay, this we do because since f is defined on the open interval from pi over 3 to pi over 2, and Riemann integrable from pi over 3 plus epsilon to pi over 2 for epsilon running from 0 to for epsilon between 0 and the upper limit minus the lower limit. And in this case, that would mean that epsilon is between that. So this one you multiply by 3, multiply by 3 out of 3, 2 out of 2, gives us 3 pi minus 2 pi, which is pi out of 6. So and then to pi over 2. One minus 2 cosine x dx. Okay. Now with this, then it's okay. Let us first do this one, and then I'm gonna state more results that we need to use here. I'm gonna state more theorems that we need to use when it comes to the improper integrals. So what we do here, we need to evaluate this integral, and then we're gonna take the limit accordingly. Okay. So to do this one, we'll let du so that we have the integral. Which is the square root of u. What is the x? It's the u divided by 2 sine x. Okay, there's a 1/2 there. With the derivative of the cosine is minus sine. Minus sine times -2, it's a 2, yeah. 1/2 here and u to the minus. So the u is 1 minus 2 cosine x. Okay, this integral is what we got, but you need to check. You can check the integral. So if you check the integral, then you're going to have d dx of this one, which is 1 minus 2 cosine. Just checking. Checking is not mandatory. It's not compulsory. And then you have cosine x to the minus 1/2, and then you find the derivative. 1 minus 2 cosine x. Okay, it's 1/2 here. And then the derivative of that, you subtract to 1, becomes minus 1/2. The derivative of the interior, it's 2 sine x. Okay, which when you multiply by the 1/2 becomes exactly that. So indeed, this integral is correct. Now, with that mentioned, we're back in business. That means when we need to evaluate the integral here, when we need to evaluate this integral, when I evaluate the integral from pi over 3 plus epsilon, minus 2 cosine x dx. So you'd have the following. Okay, yeah. So we know that then we actually proceed to take the limit and yeah, I can put the limit straight away here. So I can take the limit as epsilon approaches 0 from the right. Pi over 3 plus epsilon pi over 2 divided by the square root 1 minus 2 cosine x dx. And so if you integrate this, you'd have, okay, this limit, because this epsilon is a positive number, add a positive number. So that's why epsilon must approach 0 from the right. So we have to limit epsilon approaches 0 from the right. Okay, the integral of this we've already got is the square root of 1 minus 2 cosine x to pi over 2. One minus 2 cosine pi over 2. One minus 2 cosine of pi over 3 plus epsilon. Pi over 2 is the cosine of pi over 2 is 0. Okay, now this one, you'll have to take the limit because of the epsilon. You have to take the limit as epsilon approaches 0, so it's going to be 0. So you could have cosine of pi over 3. Okay, and then what is this? This the 4 becomes 1 minus 0, and then the square root of 1 is 1. One half. Which is 0, and then it is 1. So that this integral itself becomes 1. So obviously, you take a look at that, you check the problem. Right, you check the problem and see that everything is done above board. And see that, yeah, the integral is 1. Okay, I feel that we can do another one. Might be divergent. Can do letter B. These ordinarily are not very long, but you just need to know the concept. Like here, this one is undefined at the weighted denominator is 0, and therefore is undefined at minus pi over 2. So to find the integral of this, would therefore integrate instead minus pi over 2, and then you can add epsilon pi over 4 e to the 10x divided by cosine squared x dx. So in the end, okay, this is what we have. So what we do, we actually, forget about the limits of integration, and we only gonna do the integration. Let u be 10x. Du is sec squared x dx. Right. Therefore, if you have the integral of e to the 10x, divide by the cosine squared x dx, which is e to the u cosine squared x dx. Dx becomes du over the secant squared, but this one is 1 over cosine squared, which is the secant squared. E to the u du over the secant squared. Right, and clearly du, we have that. So we have this. Okay. So now which is minus pi over 2 pi over 4. Okay, yeah. So the u is the tangent, so that it's e to the tangent plus c. Okay, and then obviously, you see, if you integrate from minus pi with epsilon, I mean minus pi over 3, no, yeah, minus pi over 2, excuse me. We're looking at this one. I was now looking at this one, but yeah, we're doing this one. So if we have e to the tangent, and then we have the cosine squared x dx, because it's undefined at minus pi over 2, because cosine of pi over 2 is 0, the denominator becomes 0. So the integral is e to the tangent of x, which is this one. We first did the integral, and then we're plugging in the limit of integration. The limit of integration minus pi over 2 with this, pi over 4 radians. E to the tan of pi over 4 minus pi over that, like that. Okay. So now, okay, this integral, then you plug in the pi over 4 minus the minus pi over 2 epsilon. Take the limit now. So you have the limit as epsilon approaches 0 from the right of the integrals, undefined at minus pi over 2. So you have minus pi over 2 plus epsilon. This might look a little bit different from maybe, your lecturer might not even be using the symbol epsilon. I'm using the symbol epsilon because of the book I use for this module. I use a book, Mathematical Analysis by Rod Hagati. Okay, this mathematical analysis. Rod Hagati is the author. So now, right, so in the end, then what is this integral? We said that this integral from minus pi over 2 plus epsilon to pi over 4 is e to the tan of pi over 4 minus e to the tan of minus pi over 2 plus epsilon. It's e to the tan to the tangent of pi over 4 minus e to the tangent minus pi over 2 plus epsilon. Pi over 4 e to the tan of pi over 2 cosine squared dx. Minus e to the tan of minus pi over 2. So this e to the tan of pi over 4, tan of 45 degrees is 1. Then this one is going to become minus infinity, because it's going to become minus the tangent of pi over 2 radians. The tangent goes out, and this is this, e to the minus infinity. This is that 1 divided by e infinity like this, which is minus 0. And therefore, this is e. As a consequence, we have the following. Therefore, or hence, and hence now we then say the integral that is wanted. Okay, the integral from e to the 10x it's e. This integral is equal to what? This integral is equal to e. Okay? Yes, the integral is equal to e. You can also see in the chart. So in other words, this integral here is equal to e. This integral here equals to 1. Okay, I think that we're going to take a break. And we will see what to do next. But we are scheduled for tomorrow morning, but I'm sure we can do more than that. Meaning we can do also at other times. But at least the 4 to 6 in the morning is a very ideal time slot for us to do something. Right. So I must thank you for joining us. It was awesome having discussion. I'm going to check on you on WhatsApp again to see if we can do extra than just the 4 to 6. But yeah, it depends on you and the time. You have other things, you have practicals, you have classes, you have lectures to attend. Right. But I must thank you for joining us. It was awesome having this discussion. I'm going to send the recording in the next couple of minutes. Yeah. But thank you for joining us and take care and goodbye. Right. Goodbye.